Okay, hello. So we're going to look at question number 3. Now, question number 3 is by far the one that's the most challenging because there's a lot of new information and there's also a graph. But please do know that this is an expectation that you should know how to do this type of question. Right? The concept might be not within the O-level syllabus, but we should be giving you enough information for you to use your skills to analyze the question. Right? So please remember what I told you before, that you should always read the question before you look at the data. So let's look at the question first. So by referring the graph, describe the trends of atomic radii. So I need to talk about trends of atomic radii. I might not know what this is. What does it mean by atomic radius or radii? For the first 18 elements, okay, in the graph above. So that means I need to refer to the graph on top. Based on the graph, predict the atomic radius of potassium. So I need to find, maybe there's a trend and then I need to sort of guess where potassium should be. And then I need to sort of explain using the atomic structure of potassium, right? And I know that potassium is from period number 1, 2, 3, 4. It's from period 4. And so it has 4 electron shells. I know potassium is from group 1, so it has 1 valence electron. So this must be a 2881. So I need to sort of explain later. Okay, so let's look at the data. So the first thing I see here is that they tell me what atomic radius is. So atomic radius is basically the size of the atom. Ionic radius is the size of the ion. All right, and then I look at this graph. First thing I see is that H and HE, this is like period 1. Then suddenly it jumps up. This is period 2. And then suddenly it jumps up again. This is period 3. Right, so we are talking about the first 18, so this will be actually all of them. Right, so I can see that this is actually group 1, and then group 2, and then this is group 3, and then group 4, so on. And then NA again, this is group 1, this is group 2, but this is period 1, this is period 2, this is period 3. Alright, so by what am I supposed to answer here? I'm supposed to describe the trend of atomic radii. So as we move from, this is the left side of the periodic table and this is the right side of the periodic table. So when I'm moving from left to right of the periodic table, the atomic radius seems to decrease. So that's the first thing I'm going to write. When moving from left to right on the periodic table, atomic radius or radii, right, decreases. So that's the first one that I see. And I know it's 2 marks, so I need to, and I see 4 lines, so I probably need to write a bit more. So from left to right, it decreased, but then I also noticed that, hey, wait, let me give you another color. Group 1 is here, group 1 is here, there seems to be an increase, right? Let's say this group 2 is here, group 2, oh, there also seems to be an increase. Group 3 also seems to be an increase. So this is what we call moving down the group, right, down the column. So let me write this, when moving down the group, atomic radii, and we can see over here the atomic radii increases. So that is the trend that you should be able to make sense of this graph over here. Alright, so now we're going to see, predict for potassium. So the explanation actually sort of let me know, potassium is in group 1. So, and it has 4 shells, right? Lithium has 2 shells because it's period 2. Sodium has 3 shells because it's period 3. And then potassium should be up here, right? It goes up and then it goes up again, right? So it must increase, right? Because it's in period 1, group 1, sorry. So over here, this value is approximately 170. This value here is approximately 190. So I can see that this is an increase of about 20 picometers, right? About 20 picometers. So looking at this trend, 170, 190, I will suspect that this is 210. So I hope you see how I decide the trend. Okay? So predict the size, so this will be 210 picometers. Please remember to give your units, and then with reference to the structure of potassium, explain your answer. So you must say that potassium K has 4 electron shells, and is from group 1. So I know that I'm looking at the trend of group 1. So K has 4 electron shells and is from group 1. So it will be bigger than a sodium atom. Alright, so that's how we determine the size of potassium. Right, so now let's look at the next part of the video, the next part of the question. Explain the trend seen in aluminum, silicon, phosphorus, sulfur, and chlorine. So we got aluminum, right? Aluminum, silicon, phosphorus, sulfur, and chlorine. So this one over here, right? You realize that it's going smaller and smaller. So how come the size of the atom keeps going smaller and smaller? Because over here, aluminum, it should be 2.8.3, this is 2.8.4, this is 2.8.5, and 2.8.6. So it all got 3 shells. So shouldn't the size remain the same, right? However, you must remember, okay, we have learned that the valence electron, let's say the valence electron is here, and let's say the nucleus is here. There's this attractive force here, if you remember, which we call the electrostatic attraction. Right? We went through this in our lessons. Right? There's this electrostatic attraction. And this electrostatic attraction is affected by 2 things. Correct? Right? It's affected by the distance. But in this case, for aluminum, silicon, phosphorus, sulfur, and chlorine, the distance is the same. Right? So the attraction should be the same. However, it's also affected by the charge. So as I go from aluminum, silicon, phosphorus, sulfur, and chlorine, the thing that changes here is the number of protons. As I go from aluminum, silicon, phosphorus, sulfur, and chlorine, right, the number of protons increases. That means the nucleus becomes more and more positive. Right? And because it's more and more positive, and since the number of shells is also the same, right, this attractive force gets stronger and stronger. So you imagine there's a magnet, right, that's attracting the electrons towards you, correct? If this magnet is getting stronger, this electron will be put ever so close, slightly closer to you, right? So how do I explain this? So since number of protons increases, right? So we must also sort of remember, we can write our explanation starting from our therefore. So you can just form this one first, since and as therefore. And what we're explaining is that we're explaining the trend. So therefore, atomic radius decreases, right? As we go from aluminum, silicon, phosphorus, sulfur, and chlorine, the atomic radius decrease. Why do atomic radius decrease? One possible reason is that the attraction between the nucleus and the valence electron increases, so it's put closer, right? So, and as valence electron is put closer to the nucleus. Why is it put closer towards nucleus? It's because due to stronger electrostatic attraction. So due to the stronger electrostatic attraction, the valence electron is put closer, and why is this electrostatic attraction stronger? It's because the number of protons increases from aluminum, silicon, phosphorus, sulfur, and chlorine. Right? So number of protons increase, the valence electron is put closer because stronger electrostatic attraction, so therefore atomic radius decrease. Right? So this section is a bit long, so and a bit more challenging. Please consider re-watching this video and try to understand this concept over here. It's quite important. Right? I'll see you in the next video for the next part of this question. Right? Bye. All the best.